Right, I want us to look at a few examples here on Euclidean geometry. Remember, looking at the diagram will be confusing. It is advisable that you think of theorems before you go to diagrams. Let's quickly revise our theorems. Remember this one. Whenever I've got a line that is drawn from the center of a circle to the midpoint of a chord, it will be perpendicular to a chord. It tells us this is 90 degrees. But if we are given 90 degrees here, and this line is coming from the center of a circle, perpendicular to a chord, it will mean that this side is equal to this side. This one, we call it the center theorem. The angle subtended by this arc at the center is twice as the angle subtended by the same arc at the circumference. In other words, if this is 100 degrees, that one will be half of that, 50 degrees. Whenever I've got a diameter, in this fourth one, an angle subtended formed by this diameter at the circumference, it will always give us 90 degrees. Look at this arc here. This arc forms this angle. The same arc forms that angle at the same segment. They're both at the major segment. Therefore, these two angles will be the same. We call them angles at the same segment. Whenever I've got a tangent, it is important also to note the way that we lay them out. All these theorems that are here, they have to deal with a circle. All the theorems that are there, they deal with a tangent. And all these theorems, they deal with cyclic quadrilaterals. So this is a tangent, and that is a chord. This angle is between a tangent and a chord. You go to the chord, it will lead you to the angle at the circumference, which is equal to this angle subtended, formed by the tangent and the chord. So the angle between a tangent and a chord is equal to the angle in the alternate segment. Whenever we've got a radius and it meets a tangent, it will always give us 90 degrees. It doesn't matter where it comes from. We can have a radius from there to there. As long as there's a tangent there, you should know that we'll get to 90 degrees. This other one also deals with a tangent. These two tangents are coming from the same point. This tangent is coming from the same point as this one. These two tangents are coming from the same point. Then they will be equal at the point of contact with the circle. These other two are called the cyclic quadrilaterals. Opposite angles of a cyclic quad, when we add them together, they will give us 180 degrees. Not only this, also these other two, like angle A plus angle C, they also give us 180 degrees. This next one, the exterior angle, this one is outside the cyclic quad. The exterior angle is equal to the interior opposite angles. So this becomes your key to unlock any cyclic geometry problem. So whenever you see the problem, don't think of it. Think of the theorems. Let's look at this one. We are given a tangent. Once you see a tangent, you think of the theorems that deals with the tangent, because those are that is where you'll find your solution. This is a tangent. What is this line called? It's a radius. So we know that if we have a radius, so if this is a radius, this is a tangent and that's a radius, where they meet will have 90 degrees. So this will be 90 degrees. This side also is 90 degrees because together, so skipelo 180 degrees. The first one, it has stolen. Find the angle BDC. BDC. That's what we're looking for. In other words, we're looking for this angle, angle D2. We're looking for this angle here, BDC. Let's check it again. BDC. That's the angle that we're looking for. How do you find that angle? All right. Let's look at one more thing here. I see a triangle here. I see a triangle DBC. I see that triangle. Triangle DBC. Triangle DBC. What is it that we notice in that triangle DBC? There's something that we're given there. We're given that side BC is the same as side DC. Remember where we started? We talked about different types of triangles. We said we've got about 6 types of triangles. And we mentioned these types of triangles, where you've got two sides, two opposite sides that are equal. What type of a triangle is this? It's an isosceles triangle. Remember, if these two sides are the same, if I go down there, those angles will also be the same. Since we're looking for this angle, and we now know that it will be equal to that angle, because these two will be base angles of our isosceles triangle. This side, the angle there, another side, their angle there. So these angles will be equal. And my angles that are opposite equal sides, they will be equal. Kumbuthi sifuna banthina, sifuna le angle D2, which we refer to as angle BDC. If singathola le angle, kobe sesiyayazi nale, because these two angles are the same. That's the idea. If we can find that angle, we can get angle D2. How can we find this angle? Let's look at what we have. What is the name of this line? It is called a tangent. What is the name of that line? It is called a chord. So we've got an angle that is between a tangent and a chord. Which theorem is that? This is the theorem 6. It's talking about the angle that is between a tangent and a chord. It will be equal to the angle in the alternate segment. This is a tangent, that's a chord. You go to the chord, you go with it to the circumference. Not anywhere else, but it should take you to the circumference. If this is a tangent and that is a chord, where do I go with my chord? To the circumference. Then that angle will be equal to that angle subtended by this chord DC. Where is this DC taking me to? It takes me to angle B. So this angle here is also equal to 40 degrees. It is important that we should note that. Number one, when we respond to number one, 1.1, we said that in angle B, this is angle B. Let's call it angle B. In triangle, okay, let me not use a triangle. Let me say angle, let me call it DBC. That angle BDC, this angle, DBC, this is the angle. It is equals to what? It is equals to this angle here, which is 40 degrees. Why are these two angles the same? Because this is the tan chord theorem that I've used. The angle that is between a tangent and a chord, it is equal to the angle in the alternate segment. I indicate what I've used the tan chord theorem. Right. Now that we know that, we know that angle BDC, this angle DBC is also equal to this angle, because these two are base angles of an isosceles triangle. So it is also equal to the angle that we're looking for, BDC. Now, if this is equal to 40 degrees and this is equal to that one, why are these two equal? Why is BDC? Why is this angle equal to this angle? Because we've got an isosceles triangle. Isosceles triangle. It is important to mention that isosceles triangle or triangle by lawyer, triangle DBC. You've got to mention that isosceles triangle so that we know ukuthi ukhuluma ngani. Since these two are the same, therefore, no angle what? BDC, the one that we're looking for, BDC, will also going to be equal to 40 degrees. This angle now, we can tell that it is equal to 40 degrees. Let's see how we started it. This is what we were given. We know that this angle is equal to that angle, but this angle is equal to this one. So if this one is 40 degrees, this one will also be equal to 40 degrees. It helps to go to your diagram sheet. We indicate it also to lead. We now know that this is 40 degrees from this one, tan chord theorem. We also know that this one is also equals to 40 degrees because of an isosceles triangle. Right, we've answered this question. Then we've got about 3 marks in the examination for that one. Let's look at the next question there. We're required to find angle C now. Angle C, it's about 2 to 3 marks also. This one, question 1.2, 1.2. All right, do we see where angle C is? It is also in this triangle. What is it that we know about triangles? Remember your background. Your grade 8, grade 9 becomes very important when it comes to circle geometry. You must know that the sum of the interior angles of a triangle are supplementary. They are equal to 180 degrees. So if this is 40, this is 40, you already have 80. To get 180, you are short of 100. Therefore, you can see what angle C is going to be. So angle C will be 100 degrees. So to write that down, we say in triangle, which triangle are we using here? DBC. In triangle DBC, you mentioned the triangle that we use so that the examiner will know exactly what you're talking about. We're going to say angle D plus angle B plus angle C is equals to 180 degrees. Reason? The sum of interior angles of a triangle. We already know this angle, which is D, and that angle, which is B. It's 40, 40. So angle C will be equals to, this is 40, that is 40. It will be 180 minus 40 plus 40, it's 80. Take it that side, it will be minus 80. Therefore, angle C is the same as 100 degrees. That's how we go about finding the angle of C. Right, remember that we are using triangle DBC. BC. But just focusing on this triangle. In this triangle, there's this angle C, and there's that angle which we'll call B, and there's this angle which we'll call D. Originally, it was D2. So it is important to note that when we add this angle plus that angle plus this angle, that will give us 180 degrees. In the very same way, then we'll be able to find angle C. This was 40, 40 plus C. Therefore, C will be equal to 100 degrees. That's how we go about finding angle C. When we move forward to find angle A, 1.3. Example 1.3, we're looking for angle A. Where is angle A? Remember, we already have this. It helps to write what we have. It is 100 degrees. We're looking for angle A now. There are so many ways of getting angle A. The beauty of mathematics. When I look at this, what do I see? What do I see here? I see a cyclic quadrilateral. What do I know about the opposite angles of a cyclic quadrilateral? They are equal to 180 degrees. What is that saying to us? Since this figure is concyclic, it's cyclic quad, it means that this angle plus that, I'm just thinking of theorems, nothing else. This angle plus this angle is 180. This angle plus this angle is 180. What are we looking for here? We're just looking for angle A. But we know that angle A plus angle C is equals to 180 degrees. Why are those two the same? Because we've got opposite angles of a cyclic quad. Opposite angles of a cyclic quad. They are supplementary. Now, do we have angle C? Yes, we do have angle C. What is the value of angle C? It is 100. Therefore, angle A will be equals to 180 degrees minus angle C. And angle A will be equals to 180 degrees minus, what is our angle C? It was 100 degrees. So it's minus 100. So angle A thus become 80 degrees. Right, that is how we go about finding angle A. Suppose I want to use another method to find angle A. If I want to use this theorem, theorem number 6, an angle between a tangent and a chord is equal to the angle in the alternate segment. Let's see if we can do that. Look at angle A. This is the chord that I want to use. The chord that forms angle A. So this is angle A. This is the chord that I want to use that forms angle A. Do we have any angle between a chord and a tangent? Yes, we do. What is the value of that angle? If we look at this angle, this whole angle here, this is 40 plus 40. So this whole angle is what? It is 80 degrees. It is between a tangent and a chord. It will be equal to the angle formed by that chord at the circumference. So if this is 80, angle A will also be equals to 80 as well, using the tan-chord theorem as well. The last question that I want us to look at is the one that is looking for angle O1. It is important that you check the position of O1. Where is O1? Remember, we already have this angle here, which is 80 degrees. We are now looking for angle O1, 1.4. We're looking for angle O1, O1. All right, this is angle O1. When I look at angle O1, I don't look at it, I think of the theorem that goes with it. Looking at the 3 theorem, angle O1 is at the center. These are the theorems that deal with the center. O1 is here at the center. The angle at the center is twice as the angle at the circumference. Since I have the angle I'm looking for the angle at the center, I check if I know the angle at the circumference. This is the chord. It forms the angle O1 at the center. The same chord forms angle A at the circumference. The same theorem as this one. The angle at the center is twice as the angle at the circumference. One angle must be at the center. The other angle must be at the circumference. Now, we know that O1, angle O1, is equals to 2 angle A. The reason we used the center theorem. Center theorem. At times, this becomes confusing. Which one is big now? Don't think that this one is bigger than this one. O1 is bigger than the other one. Why then I say this one is 2 times the other one? I'm not saying that, but I'm saying that if I want to equate the 2 angles, I've got to multiply this by 2 so that they will be the same. I've used equal sign here. Therefore, if I want to equate O and A1 and A, I've got to multiply A by 2 so that these 2 will be the same. Now I'm saying they are equal. I don't necessarily mean that this one is the same as this one, but for these 2 to be the same, I've got to multiply that by 2. Let's move on. Do we know angle A? Yes, we do know. We've just calculated angle A here as 80 degrees. Let's substitute it in there. Therefore, angle O1 will then be equals to angle 2 of angle A of 80. What is 2 times 80? Then O1 will be equals to 160 degrees. That's how we go about solving this. Remember, this and only this. You don't think of the diagram. When you look at the diagram, it will confuse you. Just think of the theorems. Just think of the theorems that will apply in that circle geometry. Remember, these ones here, they deal with the circle. These ones here, they deal with the tangent. And these ones here, they will be dealing with the cyclic quadrilaterals. Thank you.